Statistical cluster and regression evaluation of friction coefficient in extremely thin diamond-like carbon films. Diamond-like carbon, DLC, films are ultra-thin, protective coatings often used in tiny mechanical systems, like those in electronics or precision instruments, to reduce wear and friction. Over time, even very small increases in friction can damage these systems and affect their performance, especially at high temperatures. This study looked at how two types of DLC films perform under such conditions. The films were made using two different methods: filtered cathodic vacuum arc, FCVA, and plasma chemical vapor deposition, P-CVD. They were applied to two types of base materials, nickel phosphorus, NiP, and silicon, Si. Researchers tested how slippery and durable the films were by measuring friction as the load, pressure, was increased and decreased, and by tracking how they held up over many back-and-forth sliding cycles. Results showed that the FCVA DLC film worked well on NiP at room temperature but performed poorly at high temperatures. At elevated heat, a protective layer on the surface was worn away, leaving the film vulnerable to damage due to the softness of the NiP underneath. On the other hand, the P-CVD DLC film maintained low friction and high durability at high temperatures, thanks to special chemical byproducts that acted like a lubricant during sliding. Interestingly, on silicon, both films' friction levels hardly changed with load. But on NiP, performance was much more affected by how much load was applied. Overall, P-CVD DLC films proved more reliable at high temperatures, showing lower friction and better wear resistance compared to FCVA DLC films, particularly on softer NiP surfaces. In simple terms, choosing the right combination of film type and base material is key for protecting tiny high-temperature machines, and P-CVD DLC films offer a strong advantage in such challenging conditions. Introduction. Diamond-like carbon, DLC, films are extremely thin protective coatings, just a few nanometers thick, about 7 layers of carbon atoms, that help reduce wear and friction in tiny mechanical systems. They are vital for applications like high-density hard drives, medical devices, and automotive components, where even microscopic wear can damage performance. In magnetic storage, for example, thinner protective films are needed to store more data, but this makes them harder to keep durable, especially at high temperatures. Two main techniques are used to make these coatings: filtered cathodic vacuum arc, FCVA, which produces very hard, dense films, and plasma chemical vapor deposition, P-CVD, which creates films with different chemical properties. To understand how these coatings perform under real-world conditions, researchers tested them on two types of base materials: hard silicon, Si, and softer nickel phosphorus, NiP, which is used in actual magnetic disks. The study measured both friction and wear at high temperatures, using precision instruments like atomic force microscopy, AFM, and friction testers. Results showed that FCVA DLC films resisted wear well at room temperature, but their performance dropped sharply when heated, especially on softer NiP. This was because a thin lubricating layer was lost at high temperatures, leaving the film vulnerable. In contrast, P-CVD DLC films actually became more durable at high temperatures, thanks to chemical reactions during sliding that produced protective, lubricating compounds. Performance also depended on the substrate. On silicon, friction levels hardly changed with applied load, but on NiP, both load and temperature had a big impact. Overall, P-CVD DLC films offered better long-term protection at high temperatures, making them a stronger choice for demanding applications like heat-assisted magnetic recording. In simple terms, the right coating-substrate pairing can make a huge difference in protecting delicate, high-performance systems from heat and wear. Conclusions. This study examined how extremely thin diamond-like carbon, DLC, coatings, just a few nanometers thick, perform when used to protect different surfaces at high temperatures. Two coating methods were compared: filtered cathodic vacuum arc, FCVA, which makes very hard but brittle films, and plasma chemical vapor deposition, P-CVD, which produces films with better self-lubricating properties. The coatings were applied to hard silicon, Si, and softer nickel phosphorus, NiP, surfaces. Tests measured hardness, elasticity, friction, and durability under increasing loads and repeated sliding. DLC films on NiP were softer and less elastic than on Si. On NIP, the FCVA film's friction rose quickly at high loads, especially at high temperatures, due to cracking caused by stress from the softer substrate. The P-CVD film was more stable, keeping low friction at high temperatures thanks to lubricating compounds formed during sliding. Statistical analysis showed that FCVA films on NIP lost durability faster under high loads and heat, while P-CVD films maintained good performance below a critical load. Overall, P-CVD coatings provided better high-temperature protection, particularly on softer materials, making them a better choice for applications like advanced data storage where durability and low friction are essential. This important article is authored by the following scientists. Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.